In this video, we're going to cover the unit circle. This topic is incredibly important because without the unit circle, you're not going to be able to solve any circular functions by hand. This video will just look at the unit circle and how it relates to circular functions. The next video will cover how we actually apply the unit circle to solving different kinds of circular functions. For those who don't know me, my name is Chris Iannazoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The coordinates of any point on the unit circle can be found by finding the sine and cosine of the corresponding angle. If you were to draw a straight line at some angle theta, then what you would find is that the line that you've drawn could be considered the hypotenuse of a triangle. By definition, the value of the hypotenuse must be 1, since the radius of our unit circle is 1. If you then revisit the trig ratios, you'll find that they simplify quite nicely if you sub in for the hypotenuse equaling 1. We can thus say that sine of theta is the opposite, and cosine of theta is the adjacent. If you look at this in terms of x and y, then you'll notice that our adjacent is just some purely horizontal length, ending at some x coordinate. Hence we can say that our adjacent side is equivalent to x. And since the adjacent is also cos theta, then we can say that cos theta is equal to x. The same is true for the opposite side, where we have a perfectly vertical length that ends at some y coordinate. Hence we can say that sine theta is equivalent to y. The unit circle is divided into 4 quadrants, just like the xy axis is. The quadrants and their boundary angles are depicted below, both on the unit circle and in a table form. Remember, 2 pi is a full revolution of our unit circle, so pi must therefore be a half revolution, and finally, pi on 2 must therefore be a quarter revolution. You'll also notice that there are coordinates attached to the end of each of those boundary angles. These are fairly simple to find because all the lengths involved are just purely horizontal or purely vertical. This is simple because our radius is 1, hence all of those lengths are going to be 1, and therefore that means that the other coordinate must therefore be 0. The reason this matters is because it allows you to evaluate circular functions without needing a calculator. For example, if I want to know sine of pi on 2, then I could look at the unit circle where it says pi on 2 and then just give the y coordinate at that spot. Or, if you prefer to use the table, then you could look for the intersection between sine and pi on 2, and just give that value instead. The other thing I want to highlight here is the fact that tan is actually undefined for some angles. This is because tan is actually just sine divided by cos, and since cos has the opportunity to become 0, then we see a divide by 0 error under those circumstances. Hence, we're going to have undefined. Additionally, you'll need to know these 3 inter-quadrant angles for sine, cos, and tan. What this means for you is that you have 3 angles that you need to memorize and 3 exact values that you also need to memorize. So here's how you can do that. All you have to do is arrange these values in a way that makes sense for the x and y coordinates at those spots. As the x values get closer to the origin, they should decrease. Hence, the largest exact value that we have, root 3 on 2, is going to go to pi on 6, since that's the furthest out. Then our next smallest is root 2 on 2, so that's going to go to pi on 4. And then finally, you're going to give the smallest one, which is a half, to pi on 3. The y coordinates are just the opposite. As you get further up the unit circle, the y values should increase. And what you'll find is that it's literally just the opposite order of the x values. What about the tan values? Well, you actually have 2 options here. The first is just to do sine divided by cos, since that's what tan is. For example, if you wanted to know what tan of pi over 6 was, you would first find sine of pi over 6, which is a half, and then cos of pi over 6, which is root 3 on 2, and then just do sine divided by cos. After simplification, you're going to get 1 on root 3, which is the tan value for pi over 6. If you don't like how long that takes, then the other alternative is just to memorize the tan values. There's only 3 of them. You've got root 3, 1, and 1 on root 3. Okay, well that's good for quadrant 1, but what about the other quadrants? How do we fill those out? The good news is that you don't have to memorize anything else to fill those quadrants out. Okay, so each quadrant has its own versions of the pi over 6, pi over 4, and pi over 3 angles. And we fill those out just by counting an anti-clockwise direction around the unit circle. Let's start with the pi over 6 angles. All this means is that you're cutting a semicircle into 6 equal parts, since pi is a half revolution. We can also keep counting these in the second half as well. Just make sure to simplify your answers at the end. Now we just do the pi over 4 ones. This means you're cutting that semicircle into 4 equal parts. Again, you go all the way around the unit circle and simplify your answers at the end. Just like that, you've placed all the angles. But what about the coordinates? The good news is that for each quadrant, the coordinates are identical. The only difference is the signs of those values. For example, notice that pi over 3 and 2 pi over 3 have the exact same coordinate, with the only exception being the fact that the x-coordinate is negative for 2 pi on 3. The sign of any coordinate is purely dictated by what quadrant it's in. This pretty much just boils down to the fact that all the x values are going to be positive on the right, negative on the left. And all the y values are going to be positive at top and negative on bottom, just like how it normally works. That's all you need to know to fill out the unit circle. So I mentioned earlier that tan doesn't appear on the unit circle. If you want to memorize those exact values but you're having trouble doing so, then my recommendation is to think in terms of gradients. This is because tan is just sine divided by cos, and if sine is the y and cos is the x, then sine divided by cos is just y over x, or another way of just expressing the gradient, rise over run. So with that in mind, we're just going to arrange the values in terms of steepness. Pi over 3 is the steepest line, so it gets the largest value, root 3. Then the next smallest is 1, next smallest is 1 over root 3. From there, you should also consider if your slope is positive or negative, and you'll find that all the slopes are going to be positive in quadrant 1 and quadrant 3, and they'll be negative in quadrant 2 and quadrant 4. The last thing we'll look at are the negative angles. The only thing that's happening here is that we're going in a clockwise direction instead of an anti-clockwise direction. I have the full negative unit circle printed here, but I don't actually recommend memorizing it. Instead, I recommend finding the positive version of your angle and then just flipping vertically. For example, if I wanted to find sine of negative 5 pi on 6, I would instead find positive 5 pi on 6 and then just flip vertically to the equivalent spot on the bottom of our unit circle. And sure enough, I found the right spot. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.